Okay, so we've done sum of forces, net force. We've looked at just finding net force. We've looked at relating that to acceleration. Here's the one quibble I have with your book. I think the Holt Physics does a great job laying this stuff out, with the exception that it doesn't. Oh, no, we did that. Have we had a concrete conversation about equal and opposite forces? I believe we have. We keep talking about the fact that if you're exerting a force on an object, the object exerts the same force back on you, but because F equals ma, if I throw this little thing, it exerts the same force back on me. I don't accelerate because I'm a whole lot more massive than this is. Okay, so we've had that talk on and off, but I wanted to make sure we explicitly addressed it. That's the click beetle problem. Here's the quibble I have with your book. They do a great job sequencing this stuff, with the exception of the fact that they don't mention that force of gravity is your weight until the fourth section of this chapter. We've been using F sub g all along. You already know that it's mg, but this is the point where we start to explicitly talk about it. And we talk about it in the context of gravity and then of other sort of everyday forces. So this is where we formally introduce normal force, though again, you've been using it. We've been talking about it. So F sub g is your weight. It's the force exerted on you by Earth's gravity. And gravity, the force of gravity, your weight changes on different planets. You would weigh less on the moon. You would weigh more on Jupiter. Your mass doesn't change. The number of kilograms that you would balance on a balance pan doesn't change, but the force of gravity on you does, based on acceleration due to gravity for the planet you're on. We could, if we were astrophysicists, designate the FG that we use. We could, if we were working on multiple planets, we would need to designate F sub g as F sub g on Earth. Since we're working entirely on Earth, we don't need to do that. Come the day when engineers are designing structures for a moon base or a Mars base, they will have to do that, because the force of gravity is different on those objects, and therefore you're going to have to account for different stresses. Normal force is the force exerted by a surface. You know this. We've been doing this. It's generally, it's equal in magnitude to gravity, and we should put a big asterisk there, which you already know, or at least FGY. So there are instances where normal force is equal to the whole of the force of gravity, and instances where it's only equal to a portion of the force of gravity. It's perpendicular to the contact surface, but it's in opposition to the direction of gravity. So these, these are nothing new. We've been working with them. This is the one that's a little bit new. So friction is the force that we're going to start to talk about and we're going to start to calculate with. And friction just opposes motion. Period. I mean, in its simplest terms, friction is a force which opposes motion. And we have two big categories of friction: static and kinetic. And you know that static is being still. Static friction is what is working when something is not moving, when it's at rest. It is what resists the start of motion. We have a sneaker on a deck board. It's not moving. Not going anywhere. If I tilt this up, is the sneaker going anywhere yet? No. What's holding it in place? Right now, if we did, I've now got this tilted a little bit. If we did a free body diagram for this, we know that we have F sub g, Fn, and we have a force of static friction pointing up the ramp. So what force, so obviously its sum of forces on the y-axis is 0. It's not levitating, it's not dropping through the board. Sum of forces on the x-axis is also what? 0. Which means what has to be equal to the force of static friction. And we usually designate force of static friction as F sub S. What two forces on that have to be equal that that sneaker is not moving down slope? Don't yell it out. Talk to the other people at your table. I heard whispers of force of gravity. Which part of the force of gravity? X. Because that's the one that's on the same plane. So we're saying as long as the sneaker isn't moving, when this thing is at a slope, force of static friction upslope, force of gravity on the X downslope have to be equal because it's 0. So I'm going to keep propping that thing up. What the heck? Okay, so I raised the angle here. This is a fairly shallow angle. I made it a little bit steeper here. What forces from picture 1, I should do that in a different color, shouldn't I? What forces from picture 1 to picture 2 have changed? Again, don't yell it out. Talk to one another. Okay, so let's walk through them. Has the normal force changed? No, normal force is the same. Has the overall force of gravity changed? Not unless I snuck bricks into that sneaker. Has the force of gravity on the X changed? Yes. Why? I'm changing my angle, and therefore and that would be the sine function. Sine of the angle is increasing. The higher I prop that board up, the more of my gravitational force is on the x-axis. Has my force of static friction changed? Yes. Because it's still not moving. So the reason we just went through all that is because Gesundheit of this one line. When the object isn't moving, even though there's an applied force, now in this case, on that slope, the applied force, I put that in air quotes, is the force of gravity on the x. But as long as the object's not moving, the force of static friction is equal to whatever the force is that would get it to move. So we really can't measure the force of static friction until the object breaks loose. And you're going to get lots of practice with this next week. We're going to do a really delightfully fun lab where you get to drag things around the building in boxes on ropes with protractors. You're going to love it. When that object is not moving, force of static friction is going to be equal. As long as it's not moving, then the net force on that axis is 0. As long as the net force on that axis is 0, force of static friction is equal to whatever the opposing force to it is. So in that case, it's gravity. In another case, it might be you pushing or pulling on it. Now, kinetic friction, F sub K, this is the other kind of friction that we talk about. It retards motion. It slows motion down. It acts in opposition to motion, but it doesn't prevent it. Is it easier to get something moving or keep it moving? Keep it moving, by far. Who here has gotten a vehicle stuck in a snowbank somewhere? Excellent. Oh, my Brazilian friends, this is a joy that you should experience before you leave here. Do you have an international driver's license?
Wait, joy?
Yes. You need to understand the physics behind this. At least once in your life, you got to get a car really good and stuck in the snow. Wouldn't you all agree that this is a life experience that they should have? Oh, come on. So who has been on the pushing end of a car stuck in the snow? Now, once you've got something moving, if you can keep it moving, that's good. Kinetic friction is lower than static friction for any pair in general. That's what we see. So once you get the car out, that's why you rock it. You build momentum to get it moving. Once you move it out, you keep it moving. You don't ever want to stop again. Okay, so what we were just saying, static friction is generally bigger than kinetic friction for any pair. And these are pairs, and you're gonna know why those are pairs shortly. Friction is all about sort of atomic level interactions between two surfaces. And there's an illustration somewhere in your book that does a really good job of showing that. Even a surface that looks pretty smooth to us, feel your desk surface, those are fairly smooth surfaces. At an atomic level, it's not perfectly smooth. And therefore, we get stuff hung up on stuff. The underside of this sneaker, things that we think of, well, that's pretty slippery for a sneaker. Things that we think of as sticky surfaces tend to have more atomic level irregularity than things that we think of as smooth. So for any surface pair, there is a coefficient of friction. And we have, as you might have guessed, coefficients of static and coefficients of kinetic friction. And they're just a ratio. So it's, for static friction, it's the ratio of the max static friction, that is the static friction in the millisecond before the object starts to move, to the normal force. And in kinetic friction, the coefficient of kinetic friction is the ratio of kinetic friction to normal force. They're pretty easy. You may have guessed that this now gives you another sort of equation to work with. Oh joy, oh delight, one more set of things to factor. So what this means is that if we know the coefficient of friction and we know the normal force, we can always calculate the force of friction. And that should, well, I made that a generic F sub F because it could, this is true for either static or kinetic friction. So we're going to go ahead and do the 4C sample problem, and then all the practice problems on 4C will be assigned. Okay, this is 4C sample. We have a crate. It's at rest. It's a 24 kilogram crate. Mass equals 24 kg. Force required to move it is 75 newtons. It takes 75 newtons of force to set the crate in motion. Find the coefficient of static friction between the crate and the floor. Is that a complete free body diagram? Heck no. What am I missing? Oh, yes. Gravity. I'll do these in all different colors. So normal force, force of gravity, Gesundheit. Force of static friction. So we're told 75 is the applied force that it takes to break this puppy loose. We want coefficient of static friction. What is that equal to? It's equal to the force of static friction max divided by normal force. Now, this is one of those that's the simplest case scenario. This thing is not on a slope. The force is not being applied on a slope. If I do sum of forces on the y, is it levitating or sinking through the surface? No. Not that they mentioned, and you'd think they'd mention something like that. Therefore, what's true? That's equal to normal force minus force of gravity, or mg. So Fn equals F sub g. Fn is equal to mass times gravity. That's going to be useful. Again, this is that geometric proof thing, and this is where it becomes important. So what we now have is something here that we can substitute into this equation. At the moment that this thing breaks free, in the millisecond before it starts to move, what is the force of static friction equal to? The amount of force that is required to break it loose is 75 newtons. The minute you apply 75 newtons of force is the point when it starts to break. This is where I think it gets a little fuzzy and a little dicey. So does that mean that it's 74.9999999 newtons is the maximum force of static friction? If you're going to go be a mechanical engineer and engineer systems, you probably need to think in that kind of granularity. For our purposes in a high school physics 1 class, we say, oh, okay, 75 newtons is where it breaks loose. That's the maximum force of static friction. So what we say is that at the point just before it breaks loose, so sort of last static moment, the force applied minus the force of static friction is going to equal 0, which means the applied force at that moment is equal to the force of static friction. So now we have the second piece that we can sub in. You're pretty much never going to have one of these problems without a sum of forces on each axis and a side equation for coefficient of friction. So now that we have all that, I'll shrink this. Because we've proved those, we can rewrite mu s equals force applied over mass gravity. Go ahead and get a raw answer. Okay, so I get mu s equals 0.3185, on and on and on, spare change. What are my units? It's a great question. Come on, Midvale. What do you think their mascot is? It's a ratio. And therefore, unitless. Ratios are always unitless. That was kind of a trick question. That's why I very intentionally didn't put the force of gravity in newtons. I put it in kilograms times meters per second squared, assuming that most of you would have a momentary brain fart after a 4-day weekend and forget that kilograms times meters per second squared is newtons. The units cancel when you do the dimensional analysis. So, and it's so hard to not write a unit, but there's no unit here. It's a unitless ratio. So mu s between these two surfaces is how many sig figs did we get? 2? 0.32? Okay. That's a reasonable coefficient of friction. The higher that coefficient of friction is, the more or less applied force it will take to move the object. Just point, up or down, more or less. More. The higher the coefficient of friction is, the more applied force is going to be necessary to get the object moving. Has anybody here ever done any rock climbing or rock wall or anything? Okay. Have you seen climbing shoes? They have this weird black rubber on the bottoms. My best friend was a pretty amazing climber. And about once a year she used to try to get me to go up a wall. I go about so far and I quit, and that's fine. But the rubber on climbing shoes is described as very sticky. It has an incredibly high coefficient of friction because you want to stick to that wall like a little fly. She also had what she called her approach shoes, and there are a couple companies that make them. And they look like a hiking sneaker, low, ankle height sneaker. But the rubber on the bottoms is that same very, very sticky rubber because they assume that you may be doing some not real climbing, but you're doing a technical route or a semi-technical route to get up to your climb. So you can very intentionally design materials with high or low coefficients of friction. Where would be a situation where you would want a very low coefficient of friction? Roller skates, skateboard wheels. And if you know anybody who's done like serious, I used to know a woman, neat lady, she was in her 70s and she was still doing competitive roller skate dancing. Like out there in her little skirt and little wheels. The wheels on her skates, she was meticulous about. because any flaw in that wheel changed the coefficient of, and she didn't know the physics behind it, but I mean, she scrubbed wheels after every event because any change in the coefficient of friction between her wheels and the floor impacted her skating. So, questions, comments, concerns? All of 4C book is assigned, and I'll have the 4C worksheet printed tomorrow. These are not terrible, so get going.